Next, we want to take a look at an exact algorithm for a traveling salesperson problem, namely a dynamic program. So what's the traveling salesperson problem again? So here I have a map of Germany. I'm in Dortmund and I want to visit all of the major cities and I want to do a tour that is as short as possible. So I have a string here which has the right length. And I'm now going through all of these cities. And I will continue, and this puzzle board here is surprisingly difficult. Actually, it's not so surprising if you know the traveling salesperson problem, because then you also know it's an NP-hard problem. So, once more, what's the problem we're looking at? We have an undirected complete graph with edge weights, and we want to find the shortest Hamiltonian circle. So, the round trip, and I'm summing up the edge weights. In this example, what is the shortest one here? Taking this edge seems like a good idea. And I might continue. Okay, so I have to be careful. If I take the 3 here, I think I would have to do this. Then I get 5, 10, 18. It would have been better to do the following. This route gives me 17. That's a problem. It's an NP-hard problem. It's in general NP-hard even to approximate. But in my setting of this board here, or more generally in the metric setting, it can be approximated, but still the problem is NP-hard. So we have an NP-hard problem. What should we do? There are various options. For some small instances, we can still use exact algorithms. For instance, a dynamic program that we're going to see next or soon. You can also use ILP formulations, so interlinear programming, and then use a corresponding solver, so Gurobi or Cplex or whatever solver you would like to use. Another good option is if you don't need to have the exact solution to go to approximation algorithms. Famously, there's a 1.5 approximation algorithm by Christofides for the metric TSP, where only recently there was tiny improvement over the 1.5. In the Euclidean setting, you can even do a Peter, so a 1 plus epsilon approximation. Alternative also, if you do not need approximations, there are also many heuristics. One I want to look at for just briefly now, nearest neighbor heuristic is maybe the simplest heuristic for the TSP. What do? We start somewhere, for instance in Dortmund. We go to the nearest city, which in my example would have been Bochum, and then from Bochum to the nearest, and so on until we visited every city that we wanted to visit. Then we go back to the start. In pseudocode, that looks like this. So first we pick an arbitrary start S. Here we go. Now we have a set of unvisited vertices. That will be U, so U does not include S, so this is notation for V without S. And as long as there's an unvisited vertex, so as long as U is not empty, we select the vertex in U which is closest to the current V. We add the corresponding edge to the tour, so here we would add that edge here, and then we will move that vertex U from, now we visited it, so we will move it from big U and make it a new vertex, current vertex V. We continue doing so until we visited everyone. At the very end, we add an edge back to S. That's the tour that we would be getting here. Quite obviously, it's not optimal. Optimal tour would have looked like this. A natural question is, how bad can this heuristic get? Maybe something for you to think about for a moment. So I have an example here where it gets pretty bad. Might be a bit confusing. It's not a metric example. So here I have an undirected graph with arbitrary edge weights. In particular, this edge up here has a very large weight here. If I now calculate how long is the tour that I get from my nearest neighbor heuristic, starting at my S here, what do I get? I do one step, one step, one step. Then my only option is going with big M back. Is there a shorter tour? Yes, there is. I can get a tour of length 6, namely this one. So this, if I make M very large, this can get arbitrarily bad, but it's not really bad news because we already know that the problem of approximating the TSP is NP hard. So at least for large N, we cannot expect anything better than this. And good news, for a metric TSP, the approximation factor is at most logarithmic. That might be still much more than you would want to have, but it's at least a start. So it's a viable heuristic, although there are other heuristics that are also fast and give shorter tours. So much about other algorithms. Now let's focus on the dynamic program by Bellman, Held and Karp. Dynamic programming, we want to make use of overlapping substructures. So this is the idea. First of all, we pick a starting vertex. I mean, we have to go through all vertices anyway, so picking a starting vertex, there's nothing we can really do wrong. Now we look for paths from S through. We are looking for a path from S through all nodes of V without S because S we already have. It will end in some vertex U. And then, so I'm looking for a short path through all other vertices. And then if I can find such a path, I still need to get back to S. Why did I describe it in this way? If I have two components here, the edge from U to S, I mean, there's not much to be calculated there. If I can compute the shortest path from S to U going through all other vertices, and I can do this for all U, then by taking this number and adding the length of the edge to it and minimize over all options of U, I can calculate the shortest tour. I mean, this is still work, and that's what we're going to look at, but that is ideal. We will want to have, we have a starting vertex, we eventually want to compute for every other vertex the shortest path to that vertex going through all other vertices. So the edges are easy, the rest, the other part, we have to compute recursively. For a dynamic program, we have to think about what are our parameters. So how do our subproblems look? The subproblems could look like I start from S, I go to some intermediate vertex V, and intermediately I visited a certain subset S. Yeah, so then I have two parameters. The vertex V I'm going to end on my subproblem, and the subset S that I have visited so far. And that's the parameters we're going to use. What we're interested in is for every subset S and every vertex V, the length of the shortest path from S to V visiting all vertices in this set S. And S is a subset of the vertices. Not including S, but S we visit because we started S. And this we can compute recursively. So let's have a look at how this looks like. The base of our recurrence is if I only have V, I mean, I say I start at S, my big S only consists of V, meaning I don't have to visit any vertices intermediately, then the shortest path is simply the edge, and the length that I get is the length of that edge. Now what happens for larger subsets S? Then I can compute it recursively, and this is the recurrence. So the optimal way of visiting big S and ending in V, starting from S. Now for this I can simply look at options for the vertex that is on the path just before V. Let's assume this vertex is U. Then I know the optimal solution. So if I know U, the optimal solution to get to V while visiting big S is an optimal solution to visit U while visiting S, now without V, and then going the last step to V. The only thing we need to do now, because we do not know you, we have to minimize this expression over all possible choices of u. And if we now have this value here calculated for all s and v, then the optimal T-splitter can simply be calculated as we kind of saw on the previous slide by trying every possible vertex v as last vertex that is visited plus the edge length of the edge back. So here we have it in pseudocode. This also to analyze the running time. So what is happening here? Essentially, we have here a loop over all subsets. I mean, what J, the role of J is I'm doing the subsets by size. First size 1, okay, size 1 is out here in the base case, you could say. And then I do size 2, size 3, size 4, and so on. But eventually, I simply go over all possible subsets. For all possible subsets, I'm also combining it with every possible choice of the vertex of a vertex V. So the number of subproblems that I have is already, so the number of subsets is 2 to the n. But I'm also combining it with every vertex, so the number of subproblems that I have is already 2 to the n times n. Now what is the running time that I get? For every subproblem, this is a calculation that I do. I'm trying every possible choice for u in S without v. So this is up to n choices, or O of n choices. I do this, I said I have 2 to the n times n subproblems. So this gives me a running time of O of 2 to the n times n squared. The space is simply the number of subproblems. That is 2 to the n times n. Here's a quick question. So do I really need to store all of the subproblems? So in principle, the answer is no. When I'm solving problems of the size j, I actually only need those of size j minus 1, so I could delete the old ones. The problem with that is if I then actually want to have the shortest tour, then at that point I will want to have all of the entries, because then I can use all of those entries to backtrack what the actual optimal tour was. So if I'm interested in the tour, I need this storage. Otherwise, there's a little bit of optimization that I could do. Let's finally look at this by an example, by the example that we've already seen. So here's my graph. Okay, I will try to draw a dynamic programming table. It is a bit difficult to draw because it's, I mean, I'm going to write all subsets into it. So we have the first row, and in the first row we want to go from from small s to all other vertices, A, B, C, D, without visiting anything in between. So then for A, I just have to look at the edge length from S to A and you get a 2 there, same for B and so on. So the first row is easy to fill, and now we have solved the problem for all one element subsets in combination with the vertices. Now, let's look at 2 element subsets. So let's assume I want to visit A, or I want to end on A, but intermediately I have visited B. How do I calculate it? And then I take the optimal solution from S that brings me to B, with nothing in between because I'm only visiting A and B. And then I still need to go to A. And then I look up from A to B. From A to B, I have the length 3. So 3 plus 4 gives me a 7. If I want to go from small s to A with C in between, then again I look up the 4 here, get from S to C, and then I look up A to C, I have a 4 here. So that gives me 8, and so on. And I can fill the second part of my table, and now I have handled all of the 2-element subsets. Now let's try 3-element subsets. So, and the first subset we're going to look at is A, B, C. So here, B, C. I'm looking at the subset A, B, C, and now assuming, so this first column always, what happens if I end on A? So I want to visit A, B, C, ending on A. What do I need to look up? I want to visit B and C. There I could either end on B or on C. If I visit B and C and end on B, then I end on B. I visited C intermediately. I know optimal tour is length 6. Now I visited A, B and C and still need to go to A. I am at B, so B to A. I have the 3 here. 3 plus 6 is 9. So 9 is at least one possible option here, but we have to check our other option. That is that the last vertex before A is actually C. I have to look here in my column for C. We're looking at the tour that visits B and C last. That one is the entry here. There is also a 6. Now I have 6. I've ended on C, but still need to go to A. This edge has length 4. 4 plus 6 would be 10. So those are the two options to choose from, 9 or 10. I take the minimum, and that's a 9. And in this way, I can again fill the whole row and have now handled all 3-element subsets. Okay, one more example. The only 4-element subset that we have is A, B, C, D, but we still have this V, which could be A, B, C, or D. So let's look at what happens if we want to end on A. Then we have to have visited B, C, and D intermediately. Okay, now I have to look at, let's say I want to visit B, C, and D, end on B, and then afterwards go to A. So I end on B, I look into this column. I have visited C and D intermediately, that is the entry here. I have a length of 13, and now I have to go from B to A. From B to A, BA is here, length 3, 13 plus 3 is 16 as one option, but alternatively I could have visited B, C, and D ending on C and then go to A. And then I have to look here, C, B, and D, 13, then go to A, 4. That gives me 17. That's not the good option. Last option is I end on D while having visited B and C. That gives me actually kind of a nice number here, namely 10. Now let's hope that from D to A it's not too far. From D to A we still need a 5. Okay, and that still gives me a 15. 15 is of those options the best. So I have a 15 here. And I can play the same game for ending on B, ending on C, and ending on D. Then I filled my complete table. Now I just have to go back to S. So what I'm looking at here is I have now a tour that visited all vertices, has a length of 15, but I'm at A and want to still go to S. I have to add the edge going to S, so this gives me a 17. Alternatively, I could have ended on B, 14. Now I still have to go to S. B is here. Going back to S plus 4 is 18. C ending on C is 13. Still going back to S is this 4 here is 17. Finally, ending on D gives me a 12, but back to S, 7, that's too expensive, that's a 19. Meaning, I will want to take either this tour or that tour. If you think about it, there's no surprise that there's at least twice the same number here, because if I have a tour, I also have a tour in the other direction. But let's take this one here. I'm ending on A, and now what I was saying, now I can start backtracking. So it means I go through that cell, and from there I can figure out that the last step must have brought me here, here, and here. And then I can read off the optimal tour, namely I went from S to C, to B, to D, to A, and back. And that's exactly the tool I'm showing you here. What have we seen here? We have seen the traveling salesperson problem, shortest round trip problem. It's an NP-hard problem. There are many algorithmic approaches. We looked briefly at the nearest neighbor heuristic, and then this dynamic program, which gives us an exponential running time, but also an exact solution.